Good afternoon to everyone. I am Enrico Boffetti, a second-year PhD student at Politecnico di Bari in the Department of Electrical and Information Engineering. I'd like to thank the Restart program for this opportunity. Today, together with my colleague Ilaria Marasco, a researcher in the same department, we will present our integrated experimental setup, which we have developed to characterize UAV equipped with metasurface systems in indoor wireless networks. So here is reported the outline of this presentation. We will start with a brief introduction to the background and motivation behind implementing this integrated experimental setup, followed by an explanation of the methodology used in its development. And finally, we will conclude the presentation by discussing future developments of the setup. So in recent years, the evolution of mobile network has radically changed the way people communicate, work, and access digital services. Each generation has introduced significant improvements in speed, latency, and capacity, meeting the needs of an increasingly connected world. Introduced around 2010, the fourth generation marked a breakthrough over previous generations by long-term evolution technology. It offered speeds up to 100 megabits per second, making possible services such as high-definition streaming video, smooth video conferencing, and advanced mobile applications. The fourth generation has also enabled the emergence of the mobile digital economy with increasingly sophisticated apps and greater adoption of the Internet of Things. The fifth generation, introduced commercially from 2020, brought three key improvements: ultra-fast transmission speeds up to 10 gigabits per second theoretically, ultra-low latency down to 1 millisecond, and the highest connection density. These features make it ideal for industrial applications, autonomous vehicles, augmented and virtual reality, and a new generation of smart devices. The 5G network is also designed to be software-defined and support network slicing or the creation of virtual networks customized for different uses. So currently in the research and development phase, with expected launch around 2030, the sixth generation represents a new frontier. It is expected to bring the ubiquitous connectivity between Earth, air, and space with the integration of satellite networks and unmanned aerial vehicles, the latter as components within the broader 6G mobile network architecture, speeds in the order of terabits per second, near instantaneous communication with sub-milliseconds latencies, the integration of artificial intelligence into the network, and providing immersive and holographic three-dimensional communication. The 6G aspires to become a smart and pervasive communications platform capable of adapting to the context and user needs, laying the foundation for an hyper-connected, sustainable, and resilient digital infrastructure. In addition to classic scenarios such as smart agriculture, smart cities, UAVs as aerial base stations, or connected users in outdoor environments, UAVs can also be employed in indoor scenarios to extend the coverage and ensure line-of-sight communications, thereby reducing link attenuation in critical situations where continuous and ultra-reliable communication is needed. For example, in autonomous warehouses where robots or IoT devices in general continuously exchange information such as to avoid collisions or coordinate tasks simultaneously, maintaining reliable communication is crucial. In fact, warehouses can frequently change their layout. For this reason, the wireless environment must also be dynamically reconfigurable. To address this challenge, we proposed in our scientific paper submitted to IEEE Internet of Things journal, as highlighted in the lower part of this slide, the use of aerial intelligent reconfigurable surfaces to support these kinds of applications. As reported in our scientific paper, many studies on the use of UAV-mounted RIS or metasurfaces are based on analytical or simulative models, neglecting all the real-world effects such as the pose of the UAV, which means its position and orientation, and the vibrations that cause in the electromagnetic spectrum frequency shifts in the maximum value of the scattering parameter. Few works have conducted the actual experimental analysis, however, neglecting the importance of the UAV metasurface system tilt angles and the aerial behavior of the UAV. For this reason, we developed a fully synchronized experimental setup to deepen the study of aerial passive metasurface by comparing its performance with the metasurface positioned in a fixed manner to quantify the impact of UAV's effect, such as wobbling, vibration, and so on. This setup allows us to characterize the electromagnetic behavior of the overall system, while also collecting the tilt angles and positions of objects within the environment in a fully synchronized manner. This slide presents a general overview of the developed experimental setup. It consists of two antennas spaced by a certain distance that are connected to a vector network analyzer, a measurement instrument used to analyze the properties of electrical networks and radio frequency components. It measures the frequency response of a network, capturing both amplitude and phase of high-frequency signals at each frequency point. These measurements are critical for understanding how a signal behaves when it passes through a component or a network of components. The VNA measures electrical network parameters such as impedance, insertion loss, return loss, and scattering parameters. The S parameters describe how a signal reflects and transmits through a device. For example, the S11 measures the reflection at the input, while the S21 measures the transmission from the input to the output. The VNA is also connected to a ground control station to collect the S parameters of the system over time. The transmitting antenna that is highlighted in blue sends the signal to the UAV equipped with the passive metasurface, which reflects it at a certain angle to the receiving antenna that is highlighted in red. To collect in real time the information about the position and orientation of the objects in the environment that are the two antennas and the UAV equipped metasurface, we used the Vicon motion capture. As it is connected to the ground control station, it enables the collection of this data. The Vicon motion capture system is also used to provide the UAV with its position and orientation information in GNSS coordinates, functioning like a GPS system. This slide shows the figure summarizing the integrated experimental setup in UML-like diagram. The Vicon PC is the workstation that is connected to the Vicon cameras through a switch. It is equipped with the Vicon tracker software, which is used to capture, visualize, and analyze motion data from Vicon cameras that track markers placed on moving objects or people, as well as the Vicon software development kit, which allows developers to interact directly with the motion capture data. Connected to the same network, there is the ground control station, which is responsible for providing the UAV with data on its pose through the MAV proxy software produced by the Vicon system in real time. Additionally, the ground control station is equipped with the real-time Vicon VNA collector module, an ad hoc module that we developed for this characterization that allows for the integrated measurement of the electromagnetic behavior of the UAV metasurface system through the VNA that is connected via an Ethernet cable, and through the Vicon system, the position and orientation of the UAV metasurface system. The VNA is connected to horn antennas through SMA cables, and its purpose is to measure the electromagnetic behavior of the system at a specific frequency range. Now we will provide more details on the Vicon motion capture system. It is an advanced motion capture system used to record and analyze the movements of people or objects in general in a three-dimensional space. It is a technology that uses an array of high-precision cameras to track the movements of reflective or active markers placed on a subject. An example is highlighted in red. These markers are detected by the cameras, which send the data to the software for processing and analysis. The Vicon motion capture system is usually used to create realistic animations in movies, video games, or television productions. Actors generally wear suits with markers, and their movements are captured and transferred to digital characters in order to animate them. It is also used to study human movement, analyze gait, posture, and body dynamics, or to create immersive and interactive experiences by tracking the user movements and integrating them into the virtual environment. Even in robotics, it is used to program and control robots, improving their interaction with the environment and humans. To determine the position and orientation of objects, the system uses the triangulation process. A sketch of the entire process is shown here. In this example, we have three cameras, each capturing the position of a marker within its field of view. Each camera generates a two-dimensional image showing the marker's position into two dimensions. Since we know the position, orientation, and the field of view of each camera, we can determine a three-dimensional vector that represents the possible location of the marker. So the marker's actual position is found at the point where these three-dimensional vectors intersect. Now, to track the position and orientation of a rigid body, we need to know 6 parameters, 3 for the position and 3 for the orientation. This gives us a total of 6 degrees of freedom. Mathematically, 3 not aligned markers are enough to determine both position and orientation. However, the markers must not be aligned because if they were, it would be impossible to figure out how the body is rotated in the space. The Vicon system, for example, requires at least 4 markers. This is because if one marker is occluded, the system can still track the body's position using the 3 remaining visible markers. The Vicon system also provides developers with the Vicon Data Stream Software Development Kit, a set of tools and libraries provided by Vicon to enable them to access and use motion capture data generated by the Vicon systems in real time. This SDK is particularly useful for integrating motion capture data into third-party applications, developing custom softwares, and improving interoperability with other systems. It is also designed to work directly with third-party software such as MATLAB and LabVIEW, or with common programming languages such as Python, C++, and .NET. Now we will discuss about the UAV used for this experimental setup. It is a do-it-yourself kit of Holybro. This kit is a lightweight and robust carbon fiber drone kit. It comes with the frame, motors, electronic speed controllers, and propellers. It is suitable with various flight controllers such as PixHawk series, Durandal, Pix32, and so on. As the flight controller unit, we choose the PixHawk 6C, that is an advanced flight controller that is designed for use in autonomous vehicles such as UAVs and also robots. It represents the latest evolution of the PixHawk family of flight controllers, and it features a microcontroller operating at up to 480 MHz with 2 MB of flash memory and 1 MB of RAM. It includes accelerometer, gyroscope sensors, redundant IMUs, and more. The selected firmware is ArduPilot, that is an open source autopilot system designed to support a wide range of autonomous vehicles, including multicopters, conventional helicopters, fixed-wing aircraft, and more. The ArduPilot project is developed by a large community, and its source code is available under the GPL 3.0 license. As power module, we choose to use the PM02 from Olibro. A power module is an electronic device used to convert one form of electrical energy into another, providing regulated power. It is designed to provide a simple 5.2 volts regulated power for the flight controller from a battery. Then, to send and receive data, we choose to use an ESP8266 that is a low-cost, low-power Wi-Fi microcontroller with several available ports. Its main purpose is to receive data from the ground control station regarding the UAV's pose, that is its position and orientation in real time, in order to emulate the behavior of traditional GPS sensors. To achieve this, a custom firmware called MAVESP8266 was installed, allowing the microcontroller to be used as a Wi-Fi bridge for the MAVLink protocol. This firmware turns the ESP8266 into a Wi-Fi access point that can transmit data using the MAVLink protocol, that is a lightweight and reliable messaging protocol used for communication between drones and between onboard drone components. It is connected to the flight controller unit by serial link through a TLM port. To integrate the metasurface on the UAV, custom mounts were created using 3D printing. With the frame we used, there were aluminum pipes arranged horizontally over the battery compartment, originally designed to attach a stereo camera or other types of cameras. We decided to take advantage of these aluminum pipes to mount our metasurface. Four inserts were made to allow attachment between the aluminum pipe and the 3D printed structure. We then built a circular pipe with a height sufficient to support the metasurface without directly touching it. To attach the metasurface to the 3D printed structure, we created also a bed of rubber hot glue to dampen the vibrations as much as possible. To improve the overall stability, we decided to print 4 additional supports mounted on the legs of the drone, providing a resting point for the metasurface and counterbalancing it from the opposite side. So now we will provide more details about the control system of the drone. Here I included several entities: the Vicon system, MAV proxy, the ESP8266, and the flight controller unit. As mentioned before, the Vicon system estimates the position and orientation of objects in the environment by tracking its group of markers. To provide this information to the drone, we used MAV proxy, that is a ground station software for UAVs that leverage the MAVLink protocol. By using a specific module of MAV proxy, we are able to receive and forward the position and orientation information to the ESP8266. This module allows us to simulate the behavior of GPS satellites. In fact, it is possible also to change the number of satellites to report in the simulated GPS message. In order to use this information provided by the ESP8266 on the flight controller, we tuned a series of parameters in the flight controller firmware. Now we will introduce some details on the developed real-time Vicon VNA collector module. That is, to develop this module, we used MATLAB software. The module can perform 2 main functions. It collects information about the electromagnetic behavior from the vector network analyzer and position and orientation data of selected objects from the Vicon system. To gather information on the scattering parameter, which is the ratio between the transmitted and received power levels, we use the VISA interface function on the selected port. In particular, the VNA is connected to the ground control station through an Ethernet cable. To gather pose data from the Vicon system, we use the Vicon data stream SDK, as mentioned before. The developed module also features a graphical interface that allows customization of parameters before starting the measurement phase. Users can manage the number of iterations to be performed and thus the duration of the measurement. Select the object to be tracked in real time and specify objects to be tracked only once while remaining fixed in the space. By pressing the Start Measure button, the module begins collecting information from the VNA and Vicon, first acquiring the position and orientation of the object to be tracked in real time, then the scattering value from the VNA, and finally the position and orientation of the object again. The time of each collected value is also recorded in order to synchronize them. Is also available a status bar displaying the current iteration relative to the total number of iterations. It's also possible to stop and save the measurements at any time by pressing the stop button. When the measurements are completed, the module saves all this information into a CSV file. At the end of this presentation, we will show a video of real-time measurement. Now I leave the floor to Ilaria Marasco, who will explain the remaining part of the integrated experimental setup. Thank you.
Good afternoon to everybody. I'm sharing the screen. Okay, it is allowed only a sharing, so Enrico, please, can you close your screen? Okay. Okay, so good afternoon again to everybody. I'm Ilaria Marasco, a researcher in Politecnico di Bari in nanophotonic and electromagnetic group. And in the second part of this presentation, I will show some details of two key components of the setup, which are the metasurface and the horn antennas. And at the end, I will show also all the experimental results that we obtained from this activity. So the starting point in the design of a metasurface is the design of the unit cell. In particular, the proposed unit cell that we realized has been simulated by means of Floquet port simulations in CST Studio under a normal incidence of a T-polarized plane wave. As you can see from this sketch, it is composed on a rectangular microstrip patch, which is connected to a lateral stub, which acts as a delay line. In fact, it is a tunable delay line, which introduces an additional phase shift by increasing the value of its length, which is the L parameter in the sketch. The parameters W and H have been chosen in order to guarantee a resonant frequency at around 9 GHz. In fact, this activity has been provided at X-band, in the X-band, so from 8 up to 12 GHz. As you can see from the plot in which we have the phase of the scattering parameter S11 versus the length of the delay line, so of the stub, it is possible to conclude that by spatially concatenating unit cells with an increasing of L values, we can achieve a constant phase gradient. So starting from this assumption, we realized a supercell composing the patterned array of our metasurface. In particular, our supercell is composed of 6 unit cells. So starting from the only microstrip, we had other elements in which the value of L, so the length of the stub, was higher. So starting from this, we realized this patterned metasurface, which works as an anomalous deflector. It means that when the metasurface is excited with an orthogonal incident plane wave with the T polarization, the metasurface reflects this wave with a reflectivity angle of 52 degrees. The entire footprint of our structure is 30 times 21 centimeter, and it is composed of the dielectric substrate made of FR4, which has a relative dielectric constant equal to 4.4 and tangent losses equal to 0.021, which is sandwiched between two 35 micrometer thick copper layers. The bottom layer acts as a mirror, while the top layer is the patterned one, which guarantees this reflectivity angle at 52 degrees as shown in this polar plot. So after the simulation step, we fabricated our metasurface with an LPKF prototyping machine. In particular, it is the Protomat S104, which is a very fast prototyping machine characterized by an high mechanical resolutions. In fact, it guarantees optimal accuracy for both drilling and milling, also for very small structures. And it is also a fully automatic prototyping machine. In fact, it is equipped with 20 tool position, and during the fabrication process in an automatic way, it changes the corresponding tool. So it can be considered as an operator-free machine. The other two key elements in this setup are the horn antennas. We have two identical horn antennas work in X-band, so again from 8 up to 12 gigahertz. And we have one transmitting antenna which is orthogonal to the metasurface, so the antenna that excites the metasurface, and a receiving one which takes the signal derived from the reflection of the metasurface itself. So they are flaring metal waveguide shaped like a horn, characterized by low loss, high directivity, and also high gain. In fact, the gain value is between 15 to 18 dB in this working frequency range. And they are characterized by a rectangular aperture measuring 6.68 centimeter times 8.89 centimeter. And these two antennas are connected by means of an SMA cable directly to the two ports of the VNA. So here again we can see the sketch of our setup, and in particular in this slide I reported a table with all the parameters that we varied during our characterization procedure. So again we have the two antennas, the transmitting one, the blue one, and here we have the passive metasurface at a certain height on the above the transmitting antenna. At a distance D, we have the receiving antenna characterized by a certain inclination angle. During the characterization procedure, we varied the displacement of both transmitting and receiving antenna along X and Y axis. We varied also the displacement of the passive metasurface along the three axes, so X, Y, and Z axis, the linear distance between transmitting and receiving antenna, the height of the passive metasurface above the TX, and both the horizontal and vertical inclination angle of the receiving antenna. So now let's start to see the results of our characterization, starting from the characterization of the fixed passive metasurface. All these measurements have been performed in the Spoke ITNTNS laboratory here in Politecnico di Bari with some equipment bought with the Restart fundings. The starting point of our characterization was the validation of the electromagnetic behavior of the metasurface by analyzing the scattering parameter S21 by varying the vertical inclination angle of the receiving antenna. And in particular, we fixed the height of the metasurface at 60 centimeter and also the distance between the two antennas, so the transmitting and the receiving antenna at 76 centimeter, and we varied the vertical inclination angle of the receiving one. As it is possible to see from this map, the S1 is enhanced as the theta, so the inclination angle increased, and we have a peak at around 50 degrees at a frequency of 9.76 gigahertz. After this value, the strength of the S1 parameter starts to decrease until 70 degrees, when we have some Fabry-Perot resonances, probably due to the reflection from the transmitting antenna. After, by fixing the optimal inclination angle of the receiving antenna, we varied the height of the metasurface above the transmitting antenna. And in this case, as h changes, the maximum of S1 parameter shifted towards higher frequency with a peak value at minus 22.49 dB at 9.76 gigahertz at an height of 57 centimeter. After we varied the distance between the two antennas. So in this case, when D varies, S21 values are observed to be higher in the range between 60 and 80 centimeter. In particular, the maximum was at 9.88 gigahertz, the amplitude was minus 23.55 at a distance D equal to 65.8 centimeter. Then we varied the displacement of the transmitting antenna along the y-axis of the metasurface. So in particular, we moved the antenna 10 centimeter in both the positive and negative direction of the y-axis. And the results reported in this map show that the maximum of the scattering parameter was at 9.54 gigahertz with an amplitude of about minus 24 dB. And this value decreases when the antenna is moved along the positive axis. So in this case, the maximum is obtained at lower frequencies. The same was performed also in the x-axis. So we consider the displacement of the transmitting antenna along the other axis. In this case, the maximum was obtained at its initial position, so when the metasurface is aligned with the center of the transmitting antenna, and the amplitude of the maximum of the scattering parameter in this case was minus 23.89 dB at 9.86 gigahertz. In addition, if we observe this map, we can note also the reciprocal behavior of our metasurface with respect to this axis. Finally, in order to estimate the three-dimensional space in which the drone can fly around the antennas, we varied not only the vertical inclination angle of the receiving antenna, but also the horizontal one. So we vary the horizontal in the range between minus 45 degree up to 45 degree, and the vertical from 0 up to 70 degree. And from these results, we can see that the receiving aperture angle of the receiving antenna is about 30 degrees. And this information is very important when we move to the characterization of the aerial passive metasurface. In fact, after this step, in which we consider the metasurface in a fixed position, we mounted the metasurface on drone. And we start our characterization by analyzing the wobbling of the drone when it is in hovering condition. So we put the drone equipped with the metasurface at a certain height. In particular, we choose the optimal height that we obtained from the previous results. And we fixed also the distance between the transmitting and the receiving antenna, and we estimate the S1 trend during the time, and it is possible to see from this color map that the S1 is consistent over time with only very few variations. Moreover, we estimate also the tilt of the drone with the metasurface, and the maximum tilt that we obtain is about 1.5 degree. And regarding the positional shift of the drone in hovering position is around maximum 3 centimeters. So starting from these considerations, we compare the results that we obtained with the passive metasurface in a fixed position with ones obtained with the aerial passive metasurface, so with the passive metasurface mounted on drone. The first results regard the comparison between the S1 parameter obtained from for different values of h, so for different value of the height of the metasurface above the transmitting antenna. And we can observe a very good agreement between these two results. In fact, in case of the fixed metasurface, the maximum was about minus 23.3 dB at 9.75 gigahertz at a height of 51 centimeter, while in case of aerial passive metasurface at the same resonant frequency, we have the maximum equal to minus 23.49 dB at a height of 52 centimeter. So very similar results. Then we varied also the position of the metasurface, so the displacement of the metasurface along the other two axes, so along both y and x-axis. Regarding the x-axis, it is possible to see from this graph that when the displacement along the y direction increased from 0, the maximum shifted to higher frequency, and this happens also in case of the fixed metasurface. So the maximum is obtained when we are at zero displacement, so at the center of the transmitting antenna. And maximum S1 is minus 24.35 for the fixed metasurface and minus 24.6 for the aerial passive metasurface, again at the same resonant frequency of 9.75 gigahertz. Finally, regarding the variation, the displacement of the x-axis, we can note that the S1 remain nearly constant from 0 to 5 centimeter for both aerial and fixed passive metasurface, Again, in this case, the maximum was around 0 displacement, so when the metasurface is centered with the transmitting antenna, and the maximum was minus 23.82 in the case of the fixed metasurface, minus 25.04 dB in the case of the aerial passive metasurface. So after the characterization of the metasurface in the three axes, so we varied the position on the three directions, we consider a three-dimensional space in order to estimate the volume in which the drone can fly for having a good value of S1 parameter. So an S1 parameter higher than minus 28 dB. And after several flight tests, we obtained a value of 24 centimeter times 35 centimeter times 69 centimeter, in which the transmitting antenna is considered as the origin of our system. So in this slide, we reported an example of a measurement. So in particular, in this example, we varied the height of the metasurface above the transmitting antenna. So in the left part, there is the real-time video of the measurement with drone. In the middle part, we have the MAV proxy software, which is the responsible for receiving the pose information from the Vicon system. Here in the background, there is the Vicon tracker software in which we can see the three objects that we are considering: the receiving antenna, the transmitting antenna, and the drone. And here there is the configuration interface of our real-time Vicon VNA collector module. So after selecting the number of iteration and after the alignment process of the drone on the metasurface, of the drone on the transmitting antenna, we start the measurements, and as you can see, we register the S21 parameter for all the frequency range during the time for each iterations, and then we consider the maximum S1 parameter at a certain frequency in order to reconstruct this plot in which we have the transmitting antenna, which is the blue one, and the receiving antenna, which is the red one. As you can see from the video, the movement of the drone is very slow in order to avoid that the wobbling and vibration can highly affect the measurement. And also you can see, as Enrico told before, the status bar of our module. So you can see the iteration that we are considering at this moment. And from this color map, it is possible to see that the values of S1 are different, are very different by changing the height of the metasurface on the transmitting antenna. So in this case, in which we have yellow, the value is high, so the signal received is higher. When it becomes purple, the signal was very low. So we register all these values in a database, and then we decide a specific frequency that we want to plot for see the results with the maximum values of S21 for that specific frequency. So after the 200 of iterations, this is the final 2D color map in which we have the maximum, in which we have the maximum of the S21 over time for all the frequency range. And then the drone comes back to its initial position. So I hope that this video was interesting for you for better understand the results and how we performed the measurement. So we can conclude this presentation with this comprehensive experimental characterization of how UFV movement and vibration influence the electromagnetic response of this passive metasurface in an indoor environment. And we can also conclude that this system of UFV assisted with the metasurfaces can enhance the received electromagnetic power, but their effectiveness is highly dependent on some factors like precise positioning, orientation relative to transmitting and receiving antenna, and also flight stability. Future activities of this setup regards the extension of our experimental setup also in outdoor scenarios by facilitating the integration between terrestrial and non-terrestrial networks, and also by considering other critical parameters like the signal-to-noise ratio, the throughput, the latency, the packet loss rate, and so on. Also, other future perspective of this activity are the substitution of the single drone with a swarm of drones, and also the introduction of the reconfigurability into the metasurface design. So I'd like to thank you, all of you, for your attention.